Now, I would like to ask this vacuum, the first question. Just doubt I'm asking, I'm not asking you to solve the problem. The mass of 2 kg moving in deep vacuum at 1000 meters per second, what is the change in momentum? So, uh, first I tried to calculate the G value. Like we have G on the earth is 9.81.
Right.
So, in such case, since the mass is moving at straight line, I tried to find out 1000 meters second as a v0, that is the orbit velocity, and try to find out the r. So the r value comes very high into something like an into 10 to the power of 28 meters. With that value, I tried to find the g value. So the g value also has come the very high into 10 to the power of 28. So that is 7.499 into 10 to the power of 28. So then kinetic energy this will be taken as a potential energy. So kinetic will be half of this, and the momentum in kg will be it will be same as the like the speed 1000 meters per second. But I'm not sure whether my approach is right or wrong.
So, is this the first
First sum of
assignment?
the experiment. Yeah, yeah.
So, actually, I'm not supposed to discuss the solution for the first assignment, but indeed, I can give you some concepts so that you can follow
Sure,
and
sure.
you
Definitely.
can get your answers right.
Yes, yes.
Okay. So, let's get started. We are around 7
Yeah,
3. Uh,
yeah.
so, let me just start with my introduction.
Okay.
I'm Ganesh Kumar. I'm a PhD student at IIT Gandhinagar. So I work in basically rocket propulsion. So where I focus on novel propellants in order to improve the performance of a rocket motors. So basically, I work on solid propellants. So before we need to understand how do you measure the performance of rocket motor. So all those things we will cover in this course. So you will get a good understanding. Basically, I try to optimize specific impulse and pressure. Uh, so more about me, I will tell you in due course of time about my research also. So as far as this course is concerned. This session is actually meant to be more interactive and uh, in order to help you to solve the your assignment questions, in order to help you to under in order to come up with more understanding about the concepts and in order to help you in solving the assignments. So this is supposed to be interactive. It is not a one way session. I won't be keep on talking. It is supposed to be two-way sessions. Please feel free to stop me at any time, and please interact as much as possible. And if you want, you can keep your mics and cameras turned on. So um, basically, uh, today what we will discuss is that I'm assuming that you already gone through the lectures of week 1 and week 2, right? So um, if you I would like to know what do you feel about the course, or like what are the things we understand till now, and what are the things um course taught us till now. So can any one of you like to share with me?
Yes, sir. It is something like in space the moment it is nothing but like a physics concerned in the space, which is concerned in the space.
Right.
How how the rockets go in space in vacuum? What will be the what is the principle of satellite movements? That is like a universal law of gravitation. So we know the principle of how the satellite moves with the gravitational energy of the Earth.
Right.
Similarly, the Earth moving around the Sun with the same gravitational force. Many planets moving around the Sun with a gravitational force, more or less like uh, concerned with the gravitational force of attraction,
Right.
which we use as a physics principle to orbit the satellites, rockets, etc.
So rightly, as you said, what we focused in this first week of lectures and first 2 weeks is that first we try to make our fundamentals uh, better. Like in terms of fundamentals, I mean physics concepts and physics uh, understanding on how the things work in space. So it is not only it works in space; it works in Earth also. So some basic laws like Newton's laws and as far as concerned with planetary motion, Kepler's laws, and the conservation of momentum, conservation of energy, how all these things is going to affect your motion in space. That is what we are trying to understand in the week one. In the week two, we went little further into rocket propulsion, basically telling how rockets work and how what is the concept behind having stages of rocket, for example, and what is the how do you apply these physics concepts into the rocket propulsion course. That is what we saw in the week two. So basically, what I will try to do is today solve five problems. So we have solidly some 1.5 hours or so. I will try to solve some five problems involving these concepts, keeping in mind that you are going to give the assignment problems in the similar fashion. All right. So what I will try to do today is uh, I will just start with our physics concepts, what we studied. So basically, my first question would be, uh, so I think everyone can view my screen, iPad screen, right?
Yes, sir.
Okay.
Yes, sir.
Thank you, Anish. So um, today, so this is my first question. So the reason for this motivation behind this question is for you to understand this momentum and momentum, impulse, and energy concepts. So that is the reason I give you. In fact, this question is going to be used further for three more questions in order for you to understand how this concept has developed into a rocket or satellite. So we'll more on that later. We'll start solving the first problem. And again, I would like to repeat: you can stop me at any time if you do not understand, and if you have any questions, you can stop me at any time, and I will be more than happy to answer. All right. So today, what we will do, the first question would be there is a cannon ball. Everyone must have seen a cannon. So from there, the military person will fire the cannon ball out of this gun, artillery gun, and then it goes through some projectile motion and it falls. So we are not interested in projectiles and all. We are interested in the impulse and momentum concepts. Right. I mean today. So here what I have is I have a cannonball uh, which has a mass of 5 kgs and it is fired from a stationary gun, which means gun is stationary. It is not moving. It is rigid and stationary. And it is fired horizontally. So we are taking. So when I say horizontally, I need to define a reference frame, right? So let me do that. Um, I have this reference frame. Okay, so let's take x to be horizontal and y to be vertical, and I have this cannon getting fired here. Means consider this as a cannon. So I have this small ball coming out with which has mass 5 kgs. Okay, and it is being fired. Okay, so it has some velocity. It is fired horizontally from the surface of Earth. So it is going to be fired along the x direction and from the surface of the Earth. So velocity is nothing but velocity of the cannon reached is 20 meters per second. Okay, so we have 20 meters per second velocity. Now this is simple only. Calculate the change in momentum of cannonball upon firing. So we need to calculate the change in momentum. So everyone knows momentum. What is momentum? Momentum is nothing but mass into velocity, right? So that we call it p. In fact, momentum is actually vector quantity. Here we are having a horizontal. We are telling it's fired horizontally, so we can simply write it to be px equal to m into vx. All right. So this is the momentum. Okay. What we are asking is the change in momentum of the cannonball upon firing. What is the change in momentum? So at t equal to 0, the ball is inside the cannon, and then at t equal to, let's say, from positive delta t, the uh, cannon has fired and the ball has reached 20 meter per second. That is the physical scenario we have here. Okay, so let's write it in terms of time. Okay, so let's just stick with x component. So uh, P at ti is nothing but p times vi, where vi is initial velocity is actually 0 meter per second. Inside the ball is inside the cannon. Okay, and then p at ti plus suddenly we fired it. So what happens? It has reached some velocity v. Okay, so that is 20 meter per second. So what would be the momentum at initially the momentum would be 0, right? And what would be the final momentum? Mass times 5 into 20, it will be kg meter per second, right? So but the question is asked, what question has asked us, what is the change in momentum? So there was a ball which has 0 momentum initially, and then I fired it, and it has attained some momentum. So what would be the change in momentum? It will be final minus initial, right? So it will be nothing but 100 kg meter per second, right? So this is the change in momentum we have been discussing. And the next question is, let the impulse exerted on the uh, cannonball. What would be the impulse?
It's a reactive force.
Right. So
Third law.
I didn't get actually. So am I audible? Am I audible? Am I breaking?
No, sir.
No, sir.
No, sir. Clear.
So someone was telling, what is impulse?
Sir, it is the rebounds of the cannon after leaving this mass of cannon. Okay, after leaving the gun. Nothing but like the action and reaction of the Newton's third law. The cannon left the gun, and as a rebound, cannon gets some impulse, an equal reaction. Am I right, sir?
So actually, when you say action and reaction, it's a force.
Yeah,
Uh,
it's a force. Yeah.
yeah. So but impulse is not a force. That's what. So
Sir,
if you have,
Rate of
impulse
change in momentum, sir.
in momentum. Change in momentum, sir.
so as rightly said, actually the impulse is change in momentum. So
Change in momentum. Okay, sir.
let's say if we plot with respect to the momentum of this ball with respect to time, what happened initially? It is 0. So this is at ti, and then what happened? Suddenly it raised to some. So this is at ti plus delta t, right? So it has raised from here to here. This change in momentum is actually the impulse. So in order to make sure that you understand it, that's why I made it as a two statements. So the two questions has the same answer. The change in momentum is actually equal to impulse. Then what is force? As you said, there should be a rebounds. It is true that when you fire a gun, there will be a rebound because you have changed the momentum of a uh, ball, right?
Yeah.
Right. Then there should be equal and opposite force on you. But we still don't know the force yet because force is not the change in momentum. Force is rate of change of momentum. So the rate at which this change in momentum is happening is what tells the force.
Yeah.
Uh, but the change in momentum, the different name for change in momentum is actually impulse. So when we talk about impulse, we just it's just nothing but the change in momentum. Where it is again is going to be 100 kg per meter per second. 100 kg meter per second. Now comes the next question. If the gun is not stationary, okay. So let's do that also. So can we get the force? So to have this change in momentum, how much force should I apply? Can anyone guess? So maybe I will show the problem statement. With this problem statement, can anyone guess how much force I should apply to have this change in momentum? So it all comes from the Newton's first law, right? So the body continues to be in a state of rest or in a motion until unless there is external force acting on it, right? So it remained in the state of rest. The ball remained in the state of rest, and now it has went into motion. So in order to change this, there should be force applied, right? But we know that momentum has changed, but do we know force? Newton's first law does it tell anything about force? It doesn't say anything about force. It just says to have the change in momentum, we should have force. But what is that force? We don't know yet. Newton's first law doesn't say. Newton's second law?
Force is equal to change of rate of movement.
Rate of change of momentum. So let's say, so Newton's second law tells what is force. So let's write force.
Equals to ma.
Right, force is equal to ma, but most accurate version is rate of change of momentum. That's what we would like to follow.
F equals to m into dv by dt.
That is also that is actually what. So F equal to m into dv by dt. So we have different answers. I wrote dp by dt. That is one of the student told that it is a rate of change of momentum, and there is one more answer ma and m dv by dt. Right. So I have three answers. All three are right actually. But what is the most general expression for force in these three?
dp by dt.
So here what did we do here is these two, we assumed mass to be constant, but mass can vary, right? In the real life situation, when you throw a ball, let's say, the ball's mass is not going to vary. But if you throw it at very relativistic speeds, like the speed of light, according to Einstein's theory of relativity, this mass is also going to change. So it's a little bit abstract concept which we don't want to discuss. So what we did here is we assumed m to be constant, right? So that's why we get m into a or m into dv by dt. Okay, so uh, this concept, so this also fails in the rocket propulsion. You know why? Because we didn't accelerate to speed of light, right? We of course we cannot accelerate to speed of light, but this fails. You know why?
Because is it because the
Fuel is
fuel
being
is
consumed.
burning and
Right.
the mass
So mass is changed due to burning of the
Right,
fuel.
right. When the fuel burns, some amount of mass is ejected. So masses keep on changing while you are accelerating the body. So there also this concept fails. So that's why it's better to stick with rate of change of momentum. That is the reason in this course particularly in mechanics we usually go with these things, but this particular course we actually stick with momentum. So let's continue writing it. So this is dp by dt, right? So dp by dt I can approximate as delta p by delta t, right? So what I know here is I know delta p, but do I know delta t? So I have fired and
No,
the
sir.
momentum has changed. Ball's momentum has changed. I know how much it has changed. With that, with this information, can I find force? That is my question. So the only quantity I know is change in momentum. So what is change in momentum? Change in momentum is so let's say if I rewrite this, it will be f times delta t, right? And what we know is this is change in momentum is nothing but impulse. So this is the relation. So in this, if I want to find f, I need to know the delta t, okay, which is not given in the question. And basically for the, let's say if you want to think about it, if a cannon is fired, let's say, then what would be the speed at which it will be firing? Maybe in probably some 1 seconds or 0.1 seconds, or maybe a few hundred milliseconds, right? So if you exactly know that time, then you can multiply it with, and then you can find the force. So that is how we find the force. But the impulse we can calculate because it's just change in momentum, right? So is that clear why we can't find force in this question? Because we don't know the delta t, right?
Yes, sir.
Yes, sir.
So now coming back to the third one, if the gun is not stationary, so here uh, what we did was the change in, yeah, if the gun is not stationary, like see, let me draw this here. So what I did here was basically this cannon is firing, but initially what I said, it is rigid, okay, which means it doesn't rebounds or it doesn't move basically, but in real cases it actually moves back, or it does all sort of dance when you fire a cannon, right? Now let's say if I do not fix it, I just fire it, okay, then what happens, it comes back, right? So now I need to know, so what if the gun is not stationary, calculate the final velocity of the gun, right? So and take the mass to be 100 kg for the gun. So let's write it. It was telling is m of this gun is actually 100 kg, okay, and then it is asking me to find the velocity of the gun. Now my question to you is, why would a gun move?
It's because of the react. It's the
The
reactive force.
recoil,
Right.
recoil from
Newton's conservation of momentum.
Newton's third law.
So
So we can equate the change in momentum of the gun and the cannon
so why we need to equate the change in momentum?
to find the velocity.
So but what is the concept? Why I need to do that?
Conservation of momentum.
Momentum is a conserved.
Momentum is conserved, right? So momentum is always conserved. So if you write it here for this system, okay. So in our case, the system is actually both cannon and the gun. Cannon ball and the gun. Okay. So initially everything is at rest. Okay. So let's write the momentum of the system. Okay. So what we did till now was the momentum of the cannonball separately, momentum of gun separately, right? Now we will write momentum of the system, which contains both cannon ball and the gun. Okay. So if I write this, so it will be uh, mass of the gun and initial velocity of the gun, right? Plus mass of the gun, mass of the ball, plus initial velocity of the ball, right? So what would this be? initially I said it would be stationary, right? So the velocities would be zero, right? Doesn't matter what is the mass. So the momentum is going to be zero, right? And similar units, kg meter per second. So now I want to similarly find the final momentum of the system, and I know that for this system momentum is conserved. So if I want to ask you, when the momentum won't be conserved, is the conservation of momentum always valid?
No, sir.
We when
In the
Uh,
presence
when
of external force, sir.
so then another question for you is, I am firing the ball, right? So I am having a action, and there is also a reaction also in the let's say the gun, right? So there is forces involved, right? So why would the conservation of momentum should be valid here?
Because those forces are internal forces, sir. We consider both as a system, the gun and the cannon.
Right. So that is important for you to understand. Thank you very much, Sai. So here, if we consider this ball separately, the ball moving with the velocity, if this is my system, okay, if this is my separate system, then the force is going to act on it, okay, which is one of the force. Let's say propulsion. This is actually propulsion. You know what propulsion force is like? You are pushing the ball outside of the gun, right? So some force is happening, some force is acting on the ball. So if you consider only ball as a system, this conservation of momentum is not valid. Instead, what is valid? Instead, Newton's second law. Using Newton's second law, you can you can simply apply Newton's second law. That's what I'm trying to say. But in the system, when we consider the this this cannon also in the system, right? When we consider this also within the system, what happens is there is this opposite force acting on it, which is also propulsion, but in the negative side, which is the reaction, right? So this is where you will apply Newton's second law of opposite action and reaction, and when there is opposite forces acting on it. But all these are happening within this big blue box, right? So all these are actually internal forces. So when there is an internal force, there is no need for a system to change its momentum. So that's why what we do is we write this system's initial momentum, system's final momentum, and we will equate it to get the final velocity. So this I wanted to tell you here. So what would be the final momentum? So it will be gun which we don't know yet, and we have this ball, and then it is going to be at 20 meters per second, right? So if I want to calculate, it's going to be 100 times Vf of gun. Uh, how much is this? 100 again, right? So if I just equate it, so system I equal to system F, 0 is equal to 100 times Vf of gun plus 100, right? So what happens? Vf of gun is just 1 meter per second. That gun has a very high mass, so it will
Sir, isn't
rebound
it
with some
minus 1?
less velocity.
Isn't
Yes,
it minus 1? Minus 1.
yeah, it should be -1. Yeah, true. Because it is going to be in opposite direction, right? So basically, if you look at it, so when there is a confusion in our direction, whether it is positive or negative, we go back to from frame of reference. So
Excuse me, sir.
right, initial would be positive, like positive x would be 20 meter per second. So Vf should be negative, it will be -1. So it will be in the negative x
So
direction.
why, so why, excuse me,
Yeah, yeah.
why ball velocity is zero, sir? Is it
So
zero?
initially, no, no, here the final velocity is 20 meters per second, right? It is given here.
Okay, okay, sir.
So initially it is zero. Initially everything is at a state of rest. Okay. So now I think it is good time to answer the final question. Is the momentum and energy conserved in the system? So when I say system here, let me be specific. It is ball, cannonball plus gun, artillery gun. Okay. So we just now equated momentum. So of course, momentum is going to be conserved. Okay. Let's write it down separately. So momentum is conserved. Now what's the energy? Is energy conserved?
Yes, sir.
How is the energy conserved?
So the potential energy has turned into kinetic.
So I have a few kinetic energies, right? So let's write it. Energy. Okay. Energy is nothing but potential energy plus kinetic energy. Let's ignore potential energy. Ignore potential energy. Do you have any questions?
No, sir.
Okay. So let's ignore potential energy for now. Okay. What is kinetic energy? Half
Half
mv square.
mv square.
Okay. Now we have energy of a system to be half mv square, right? So this is energy of a system. So what is the system we have? Half the gun and v of gun square plus half of m. What is the other one? The ball and your ball square, right? This is the energy. So initial energy. What is initial energy? Initial kinetic energy.
Zero.
Zero.
Okay. So what is the final energy? Energy of conservation should be means EI should be zero. EI should be equal to EF, right? This is the conservation of energy, right? Isn't it?
Yes, sir.
Yes,
Yes,
sir.
Right.
sir.
Now find the final energy. What is the final energy? Do we have V of gun?
It is also zero.
How can it is zero?
Because half m gun v gun square is minus 100,
Mm-hmm.
minus 50, and the other one is plus 50.
Okay. It's better to write down the expressions fully so that we won't confuse ourselves. Okay. So it is 20 square, right? So let's do the math. Minus 1 is 1, right? It's not, it's no more minus. And it is 50 plus this is 20 square is 400, is it? 400 by 2, 200, 200 into 5000, right? Am I right?
Okay.
This doesn't looks like EI equal to EF. Does it?
No, sir.
We're going wrong. Is energy conserved?
Sir, this is EI plus EF should be EI plus EF.
Sir, we just considered kinetic energy. I
Okay.
mean, there must be some fuel, right? Like from chemical to mechanical work done. So,
Right.
Sir, EI plus EF should be equal to the rebound energy.
Rebound energy. So why
Yes.
is it only rebound energy?
Uh,
what sorry,
At the
okay,
same
okay.
time, we could also have considered the heat energy, how the cannon is fired. We should know first how the cannon is fired by heat energy.
Right, right,
So that heat energy converted into kinetic energy, and the kinetic energy is rebound. That is as usual by Newton's law of third law.
right, right. So that is where I am coming here. So here we
Here,
considered.
yeah, it is EI plus EF is the total energy. It cannot be EI is equal to EF is not correct.
Okay, so when I say EI is nothing but initial energy system. So
Hmm.
at t equal to 0, I have some energy, and at t equal to some t plus delta t, I have some other energy. So when I say conservation of energy at during a process or something, we initial energy and final energy should be same. That is what conservation of energy means, right?
Okay.
So when we say momentum, conservation of momentum, let's go back on the momentum. What we did here was initial momentum and final momentum is same, right? Based on that only we applied this concept and we obtained the velocity, right? Similarly, energy, initial energy and final energy should be same. That is what conservation of energy means. But here, what we did was we considered only kinetic energy. What we internally missed is when you fire a cannonball, there's going to be basically a gunpowder or something which is inside, which explodes. In fact, combustion happens inside. And then, based on this combustion, this chemical energy stored within the fuel, as you said, it gets converted into uh,
Heat energy.
right. It is not exactly converted into heat energy because heat energy is going to get indeed heat energy is going to get converted, but it is not going to propel your ball within the cannon. What is going to propel is the kinetic energy which is of the gases which is present inside upon combustion. But heat energy is dissipated in the gun. So heat energy dissipates within the gun. It is not going to push the ball forward. That is what I meant. But when there is a combustion happens, um, this energy, heat energy, and the kinetic energy gets generated, and it pushes the ball outside. So that's why we are not getting this conservation of energy if we do like this, because we didn't consider the full energy components within it. Here EI is not exactly zero because but it has some chemical energy, right? In fact, it has a
Yes,
fuel.
yes.
And then this E final is not going to be 150 joules, it's going to be plus some heat energy, as you said. There's going to be some heat energy, and when we compare these two, it's going to and these two going to be same. Basically, energy is conserved everywhere. That is what I want to make sure here. So, if this concept is clear, we can go to the next question, which is a little bit further interesting. So, if you have any questions, you can ask me.
Now, what we have studied here,
Mm-hmm.
calculating the momentum, is based on the which is on the Earth. Same thing if it is considered on the vacuum, deep vacuum, or in space. Where there is a gravitational force of attraction only is stands. But here, this is on the Earth, so we can just calculate with a simple formula. But same thing, suppose if I do in space, like a satellite or something like that. So I don't know. Suppose one object, one asteroid or a satellite is moving at a certain velocity. It is only due to force of gravitational force of attraction. So in such case, how to calculate the momentum and other thing that
Right,
apply.
right. True. So, one important thing that we assumed here, can you guys guess? So, here I told that it is going to be horizontal. We didn't consider gravity here. Is gravity acting on the ball?
No,
Why is it
this
not?
is
it's acting, sir, because we are firing from the surface only, Earth surface only. No?
I'm going to fire it on the surface of the earth, right?
Yes, sir, yes.
So
So
if the
the
if
gravity is there.
right, so but along the x direction there is no gravity because I'm on the surface and I'm going to fire horizontally. Uh, the so there is gravity is acting vertically, right? Along the x. So what we did here till now is actually, if you look at it, we used px, x component of momentum, right? Everything we did till now is just x component. The gravity doesn't really come into the picture, which we see it in the next question. But uh, so in the space, to answer your question, in the space, what is actually space? So is this whatever analysis we did? Let's say let's do this. Let's take this Canon gun system, and then we will go to the space somewhere in the deep space, uh, and then okay. So what are all the what is the momentum you will get? So anyway, this is going to stand the same, right? 20 meters per second, and mass is going to be 5 kg, right? The momentum is just mass times velocity. It doesn't tell uh, which force is acting on me in order to change my momentum. So there are multiple forces acting on the body, and the momentum doesn't tell which force is acting on the body. It just tells I have the mass and I am moving it with some velocity, right? Then in that case, what is the momentum? If you ask me, it's just mass times velocity. Whether you are in space or whether you are in earth doesn't matter, right? Because momentum is just mass times velocity. So in the space, in addition, what we did was we assumed that yeah. So if we go to the next question, it would be more clear how this is going. So I would request you to wait for some time.
Sure.
So let's go to the second question. In that, I have this same Canon gun system. Okay, so I just want to stick with one system in order to both cover your understanding and your solving skills. So that's why I stick with the same kind of problem. Here I have same system, but the gun is present at some hill. Okay, altitude of 5 kilometers, which means it is above the hill of which has altitude of 5 kilometers, and then similarly I'm horizontally firing the uh, cannonball. So let's draw our frame of reference, which is very important. So here again I have y and x, some hill which is some 5 kilometers. Is it 5 kilometers? Yeah. So and then I have this cannon system. Then it's going to fire the ball. Okay, and that ball is going to be have some velocity. Okay, so and it again fired with the same velocity, let's say 20 meters per second, doesn't matter where is it. It has same propulsion system, it's going to fire with the same velocity. Okay, so now I'm asking, what is the horizontal distance it travels? So what happens if you fire the ball? What happens to that state? So we calculated the momentum till this state, so till t plus delta t. So what we did was at t equal to t naught, or let's stick with 0 seconds. At t equal to 0 seconds we fired, okay, or we pulled the trigger, and then at t equal to t plus some delta t, or it's just delta t seconds, for a very small second, this ball came out with 20 meters per second, right? Now t greater than delta t, what happens? What is going to happen to the ball?
So it will follow projectile path.
So projectile path. What is projectile path? I don't know what is projectile path.
It has both kinetic energy and potential energy. The
Right.
ball, yeah,
We have
ball
both potential energy and kinetic energy.
kinetic energy.
Okay.
Potential energy because of the height altitude, and kinetic energy because of the firing.
Okay. That is fine. But what is going to happen to the ball? It is here. Is it going to move forward? It is going to drop down? It is going to go
Or
upwards?
it
But
will
it will
go
move
in
in both x and y direction.
projectile motion.
Okay, so maybe I will. Let me ask: is this projectile motion? Is this how it goes?
Yes, sir.
Yes, sir.
Sir,
Sir, we cannot say projectile. It depends on the target. Suppose target is straight, and suppose it hit the target, we can say it moved straight only in the same straight direction only.
Okay.
But if there is no target to hit, then it will take a form of projectile.
Okay. So who decides what is target?
Velocity?
Velocity decides what is target. So let's consider. So uh,
so
understand
Anil,
what do you mean by target? Is that means like I have something to
Yeah.
hit on here?
Yes. Something to hit.
Okay.
Some other. Yes.
Okay. So I have some house here. I just want to hit that. Okay.
Yes.
Now,
Yes.
so I have a target. So it is also horizontal. Let's say above a hill. Okay. Above 5 kilometers. Okay. Now, if I fire the gun with 20 meter per second, will it go and hit the house what I draw?
Mhm.
So let's
Here, sir. Here, force of gravity comes into picture.
right. So
Gravitational.
okay, let's write down the forces. Okay, after it
Yeah.
came out, forces we have. So it came out with some velocity. Now it is moving with some constant velocity. This v is there, constant velocity, which is at the height of 5 kilometers from ground. Now, what are the forces acting on this cannon, cannonball? Let's just write that first.
So gravitational force will act.
Okay, because Earth is keep on pulling down, right? Things. What else? Is there any other force acting on it?
so maybe frictional forces like drag.
Okay, there is drag. There is a new term drag. Let's not go into
Yeah.
drag.
That is negligible. I can say it's negligible because the area is very less.
So let's write it like air resistance, and then we will ignore it. Okay. So
Okay.
there is some air because air is we are moving through a medium, right? So there is this air resistance which is actually drag. True. And what we do here is we will. Okay, probably I didn't write it. Um, Maybe what we do is we will neglect it. It's very small. Okay. What is there?
Normal force.
The normal force here. In the sense normal to y, normal to x.
Sir, Coriolis force.
Coriolis force. Why there should be a Coriolis force? What is Coriolis force? I don't know what is Coriolis force. It's just
Yes.
okay.
Uh,
Haha. So whenever we think of something, which I would like to tell here is, whenever we think of something, let's think logically. Let's forget whatever we learned till now. Okay. So let's not think that okay we studied some Coriolis force, we studied pseudo force, we studied these many forces, those things will act. So let's forget what we studied. We just think logically. There is a ball coming out. So what would happen to that? Let's say I'm throwing a ball from here. So what happened
Impact
to that?
force. Sir, impact force.
Okay, what is impact force? There are new forces coming into picture. I don't know what is impact force.
Reaction.
What is reaction?
Sir, only gravitational force acts, sir. No other force, but
So
gravitational force because of which it takes a projectile.
right. So in fact, if you see this gravitational force, so if there is a ball I'm throwing out, so it ultimately reaches ground, which means there's something pulling that ball to down. Okay, if I, let's say, in deep space in the sense there is no gravity at all. So there are these big heavenly bodies like Earth and Jupiter, and I'm not near any of that. I'm in somewhere in the deep space where there is no mass around me. Okay, and I have all there with some velocity 20 meters per second, right? So when I did that, there is no gravity. There's no force acting on this ball. So what happens? It continues to move in that with 20 meters per second throughout. Okay, but here in this Earth, what
Sir,
we
can you
have
repeat,
is
sir? Can you repeat? Can you repeat, sir?
yeah. So when I say uh, deep space in the sense, I am actually not near any of the planets or stars like Earth or Jupiter or whatever. I'm in somewhere which is empty void. It's just space, and
Yeah,
I'm
like
just
I can understand like this. Now, Earth revolves around Sun with a gravitational force.
right.
So, an object moving in deep space means it has no gravitational force of attraction. It
True.
is how it is moving. We don't know.
We don't know. It won't move. In fact, if it doesn't have velocity, it is not going to move. So if you impart, let's say if you throw a ball there in that deep space with some
Okay.
velocity 20 meter per second, there
Okay.
is no force acting on this ball which can reduce or increase its motion. That is what Newton's first law tells. Like it is continues to be in the state of rest or motion until well there is an external force acting on it, right? So it will keep on moving with 20 meters per second or uh, yeah, so with whichever velocity you are putting on it, right? Since there is no gravity, it is not going to get attracted, it is not going to move anywhere. So there should be some external force acting on it. But here in this problem, if we see, there is a ball thrown out with some velocity 20 meter per second, but what we have is something is pulling down, which we actually see, right? When we throw the ball, it is going down, it is not going straight,
Yes.
right? Which means something is pulling. What we call that pulling force? We call it gravity,
Gravity.
right? So, so this is going to fall down. So why not it falls down like this? It, yeah. So why not it falls down like this? Why not it can go and it can go straight line and then fall down? Why can't it do that? Why can't it just simply fall down? Yeah, it reaches down with the
Sir,
acceleration of
because it has a horizontal velocity of 20.
exactly. So what we have is we have it is falling down. That is important. So it is falling down, but it is in the y direction, right? So it is going to fall down. It is in the y direction, but what it also has is the x component of velocity. So something which is moving, and I keep on pulling. So what happens? It just goes down like this. That's all. It just goes like a curved path, but we don't know what is that curve. Or let's let's do this. Um, this ball which is moving at 20 meters per second, right? Now I have uh, gravity acting on it, Fg. Let me write it in a different color. I have a gravity acting on it, Fg, right? So what happens? It keeps on pulling it. Okay, this is Vx. This is Vx. So and then this is going to acting perpendicularly down. So there's going to be Vy velocity, right? So here, um, along the x direction, is there any force that is important?
No, sir.
No. So because there will be force, which would be air resistant, but we neglected it, right?
Yes, sir.
Right. So since we neglected it, along the x direction there is no force, right? In along y direction, what we have is that pulling force called gravity. So now, if we carry out this, so some people said it will be projectile motion. I'm not sure what is projectile motion. Basically, I know what is projectile motion, but I don't want to go into those topics. Projectile motion. What I would do is I will do simply analysis. There is this force acting down. What Newton's second law says? Newton's second law says F is equal to ma, right? Or let's say dp by dt, where both are vectors, right? So if I write in x component, what happens? dpx by dt, right? What is along x direction? There is no force, which is 0, right? Then what this means, then delta px is 0, which means momentum is constant along x direction. I didn't talk about y direction yet. Let's write for y, fy, right? So what is fy? Fy we have fg. There is a gravity force acting on it. So what we will write? We can write it like m into g. So this we can write it like, so we have something dpy by dt equal to mg, right? Here I'm again assuming I'm going to assume m is constant, right? So if I assume m is constant, what happens? M dvy by dt is equal to mg, right? So m and m gets cancelled. So what happens then? Dvy by dt equal to g, right? So if I continue this, dvy is equal to g dt, and then I can integrate it, right? So if I integrate, what happens? Times gt plus c. Initially, when I at y equal to, let's say, some 5 kilometers, I don't have any, so we'll write t equal to 0. I have a velocity to be 0. I don't have y component velocity. When the cannon is fired, it fires in the x direction. It doesn't fire in the y direction. It doesn't have any inclination to have a y directional velocity, right? Then my initial velocity is 0. So if I substitute that here, what happens? Vy is going to be nothing but gt. So there is this y velocity, and it is going to keep on varying, because it is going to keep on varying with respect to time, because there is an acceleration. Only when there is acceleration, the momentum of the ball changes, momentum of a system changes, and that acceleration here is provided by gravity, and the expression for velocity of y is v times gt. Okay, it is as simple as this. You just need to apply your logic. You don't need any hi-fi physics. Now we have vy equal to gt, right? And what we have this px equal to constant, which means m into vx equal to constant, right? So m is, we know, already constant, then vx also should be constant. And what is that constant? We initially fired with 20 meters per second. So your whole motion of the ball is actually governed by these two things, 20 meters per second, and vy is g 9.81 into t meters per second. That's all. You no need to go into any projectile motion concepts, and you need to apply anything. You just need to apply Newton's second law in separately from x and y direction, and you will end up with these velocities. Now, so is that clear? Is anyone missing out what I'm trying to say?
No, sir.
So if I continue this, let's say I have to calculate the horizontal distance traveled. So how do you calculate horizontal distance traveled? This horizontal distance traveled in the terms like, since you guys are very familiar with projectile, you can say it is a range. But let's not go into projectile concepts. Let's just stick into what is the horizontal distance traveled, or let's say L, okay, along length. So from here to here, what is this length traveled? Is what I'm asking, okay? And what this L is getting, how L is getting, governs this L factor? Can you guys guess? So I'm having
Time.
some
X component.
uh-huh,
Velocity along X.
velocity along X only is going to govern. Velocity along Y is going to govern Y direction, right? But one more question: if only velocity X is governing, how do, like, since I have no force acting on the X direction, how do you expect it will reach ground? So
Time.
I'm telling it will reach ground, and I need to know exactly the point where it reaches ground. So to reach ground, what I should do?
Velocity of zero.
What? Can you come again?
Velocity is zero. When it is reach to the ground, final velocity is zero.
Zero. Um, which velocity? X direction or Y direction? We have two
No,
velocities.
y direction, vertical velocity.
Vertical velocity should be zero when it reaches ground. Is that?
Yeah.
See, okay. Let's think like this. I have this system again, and initially I'm having Vy to be zero. That is true, right? So because I'm firing at X direction, right? So I have Vy which is equal to 0 meters per second. Okay, that's all. The system is simple. I have Vy which is 0 meter per second, and I am what to calculate when it reaches ground. And you need to understand there is a force acting. There's a gravity force acting which is keep on pulling the object, right? And initially it is 0 meter per second. And what we know is when there is a force acting, this ball velocity should change, right? Its momentum should change, right? So if you tell that it reaches the ground with 0 meters per second, then the velocity difference is zero, right? Then where this force is going? So if there is a force, there should be change in momentum. And
Sir,
initially,
it follows the parabolic path.
so I am planning to find what is that parabolic path. How do we find that parabolic path? I don't know whether it is parabolic. How do we know it is parabolic? It can be
So
elliptical.
component along X.
I didn't get it.
So the time it takes to fall onto the ground will be same to it will travel in the X direction.
Right. So if you think I have a ball and it is moving with some X direction initially, and there is no Y direction, and I have force only in the Y direction, which means it should drop down. But when it drops down, it cannot remain with 0 meters per second throughout, right? Because it is varying, it is dropping down. Then it has to the velocity along Y direction should increase, right? And we also seen that what our equation says, as time increases, this is going to drop down. The ball is going to drop down and it is going to come to the ground. But in X direction, the velocity doesn't change. It's just 20 meters per second, right? So what happens? It as 20 meters per second is maintained, it keeps on decelerating. I mean, keeps on coming down, and it reaches down. Okay, so at some point it reaches ground, but we don't know whether the velocity is zero or not. We cannot say as it reaches ground it will be zero. When we throw the ball, when it is going to go down and it doesn't stay there, it just jumps up, right? So if it is zero velocity at the ground, then why it will jump up? I understand you it will go decelerate to zero, and there will be a reaction force from the ground, and that will go up. But we are not interested in those rebound in things. I just want to know where it touches the ground, right? If you just want to know
So
where it
we may
touches the
need to
ground,
write an equation for the curve. There should be some equation exist for the curve, like the projectile.
Sir, can we
true.
integrate this equation for Vx and Vy?
Yeah, you can do that. So let's say Vx equal to the I will come to that curve. How come we will get that equation? It actually
Yeah.
comes from this concept. So when we say it is dx by dt, we know velocity is nothing but displacement, right? Change in displacement, rate of change of displacement, which is equal to 20 meters per second, right? And similarly, we have Vy, which is also dy by dt. In this case, x is a function of t and y is a function of t, because that is what tells us how x is going to vary and how y is going to vary. And when you couple these two, you will get your this curves equation, right? We no need to give equation as a input to the system in order to get the solution. We will get the solution, and the solution is the equation, the curve equation. So we will see that also. First we will try to understand where it hits the ground. So dy by dt is nothing but 9.81 t, right? Then this is not very interesting. It's going to be um, x 2. uh, let's come back to this equation later. We will go to this equation Vy. Okay, so we will have dy is equal to 9.81 t d. We will just integrate it, and we will integrate kilometers to zero, right? It has to reach the ground. We have to reach the ground. And one more thing we need to note is, we will find out there is a flaw in this equation. We will find out that. So this is why um, y varies from 5 to 0, right? Which is equal to 9.81 t square by 2 from 0 to some time t. Okay, then what happens? 0 minus 5 is equal to 9.81 t square by 2. Okay, then what happens? Minus 5 into 2 divided by 9.81 is equal to t square, and it is time is imaginary. Did we do something wrong? From time be imaginary, it should be real, right? What we did here was,
Vy is equal to integral of that's yeah.
Sir,
There you
we
did
have
mistake
we
again.
have
mhm, please go ahead.
Like you have integrated that Vy is equal to dy into dt,
Sir, we
and
have to
then
integrate from
again you
0 to 5, not
integrate.
5 to 0.
Why it should be
Sorry,
0
sir.
t?
5 to 0, 5 to 0, correct.
Right, 5 to 0 only I should integrate.
Yeah, correct, correct.
Then what happened here? Yeah, someone was telling something. What was that? Integrate?
You integrated twice, like dy integral of dy is equal to 9.81 into t into dt. That was wrong.
Okay, what should be? Integral of
Uh,
integral of dy is
integral
equal.
of du.
This is the equation, right?
Yes, 9.81.
9.81 times t times dt integral. This is what I am getting, isn't
Oh,
it?
right.
That's a downward side and length is expected to be negative.
Right. So what we did here was we did this mistake. When we write our equations, we need to be very careful about the directions, because we are resolving each and every direction. Actually, gravity is the downward acting force, so it should be minus Fg, right? If it is minus Fg, it's going to be minus mg, it's going to be minus g, it's going to be minus, and finally this is going to be minus, and this is minus, this is minus, and then this is minus, so become plus. Okay. So what is this time is going to become? 10 by, let's say 10, around 10 by 9 point. Which is the, I'm getting around some 1.2 seconds something. So what this tells is, I'm going to, in 1.02 seconds, I'm going to reach ground. Okay. And one more thing, this is 5 kilometers, right? This is 5 kilometers, so you should be careful. 10 power 3.
Or wouldn't it be square root of 1.02?
So, yeah, but it is 5 kilometers, right? How much is that? You need to convert
So
into
it is
meters.
102 seconds.
Right. So we have 102 something seconds. Okay. So it's going to take 102 seconds to come down and reach the ground. But we still don't know where it reaches the ground. Right? How do we do that? That's when we use the second equation. This equation. So because x direction is what tells what is the range at which point I'm dropping down, right? So if I use dx by dt, which is equal to 20, and how does x varies? X varies from 0 to this L, right? So if I do that, yeah,
Sir, I have a doubt in the previous step. So we equated t is equal to square root of 5 into 10, 5 into 2 into 10 raised to. Then why is the answer 102 seconds? Because it should be under root of it, right?
is the answer 102 seconds?
So the
How much are you
answer
getting? I'm not sure.
for
I don't have.
time would be equal to square root of 1019.3.
What is the answer you are getting?
So I'm getting 31.92 seconds.
31.92 seconds. Please check which is right. But calculate it, I think 31.5 into 2 into 10 power 3 divided by 9.81 square root of. Yeah. So I'm also getting 31.92. So let's say some at time t seconds it's coming down. Okay. That time is 31.92 seconds. So what we do integration here, it goes from 0, we will reach where it will reach, some length L, right, which is what we need. And then from t equal to 0 to some t, right? So this gives us x 0 to L 20 times t 0 to t, right? And then I have L minus 0 equal to 20 t, right? So L is equal to 20 t. Let's say if the t is 31.92 seconds, I'm going to reach at 638.4 meters. So we no need to know what is projectile motion in order to find out where I will drop down. We just need to know Newton's second law. Okay, Newton's second law will tell, you just need to resolve x and y direction, and you apply Newton's second law to these directions separately, considering the forces properly. That's all. You will know where it reaches down, or uh, it goes, at what time it reaches down. So the one thing to note here is, it takes 638.4 meters. Okay, so this L is actually 638.4, whatever the length you are getting. This is what I'm getting, um, but the concept should be clear. So now, what was the, so this is what we need to find. What is the horizontal distance with which it drops down? 638.4. Okay, now let's say I have another interesting statement here. A powerful propulsion system is installed on the gun. Okay, so initially there was some propulsion system which can increase the velocity to 20 meters per second. Now I have changed the propulsion system. most full powerful propulsion system, okay, is installed on the gun, which can accelerate the cannonball up to velocity of 20 kilometers per second. So from 20 meters per second, I can accelerate to 20 kilometers per second, which is very high, which is it's not possible. There is no such propulsion system yet. But for the sake of understanding of concepts, I want to emphasize this question here. So, and then now calculate the horizontal distance traveled by the cannon ball before it hits ground. So we will use the same equations. What are the equations we have? We have two equations. One is this dy by dt is equal to 9.81 t. Then dx by dt is equal to some velocity. Okay, we will use these two equations. We no need to derive it yet because these two are general equations. Okay, now please tell me, let me write it down again. So please tell me uh, what would happen. Maybe you can calculate and tell me, right? It's just change in velocity. You can tell me what is the length which with which it travels, or length which at where it drops down. So now I have, remember it is 200 kilometers per second, which means nothing but 200 into 10 power 3 meters per second. If you plug in these things into this equation, what would be the velocity you are, what is the length you get, the range with which it drops?
6,000
Understanding.
6,385.5 kilometers.
Meters or meters?
Kilometers.
Very good. Kilometers. We have some answer 385.5 kilometers. Okay. Now, please understand something. So we are telling you we are uh, firing at 5 kilometers, right? And the equation gives us is just some kilometers, some 6,385 kilometers. So will it travel in straight line till 6,003? I mean, will it travel in this projectile motion till 6,385.5 kilometers?
Sir, here time actually we have to consider whether it is the same.
Of course, it is not same, right? Will it be
Yeah.
same?
No, if it is not same, then yeah.
So let's calculate it. Let's find it. It's not a problem. Dy by is zero point 0.8 times t dt, right? And then we again from 5 kilometer only we are firing 5 to 0. Then we are going from 0 to t, right? So what happens? It looks like the same equation before, right?
That's why, yeah.
So the time will be same, like 31.92 seconds or 1 or 2 seconds. There were two kinds of solution. Whichever second, time will remain same, but the velocity has changed, right? So anyway, the underlying concept is this is the equation you are going to consider, even if the velocity is going to change, because the velocity of x direction is going to come in this in the x momentum equation, or I mean dx by dt equation. Okay. So if we consider that, let's put that here again. Uh, if you put that here, you are going to get dx equal to vx time dt, right? The time is x is going to be vx time t. The time is going to be now I have 200 into 10 power 3 into 31.92 seconds. So it looks like I'm also getting 683.0 kilometers.
Si-
6384.0 kilometers.
63.84 into 10 to the power
Yeah,
5. 10 to the power
right.
5
Yeah.
meters. So if you convert into kilometers, 6384 kilometers.
True. Right. So now can anyone tell me what is the radius of Earth?
64,000 kilometers.
64,000 kilometers.
No, 6
6,400, sir.
6400.
6,400 kilometers.
Okay.
Right? It looks like you are firing and then it almost went to one round and it came back. Is it what happening?
No, sir.
Happens, it should fall down, right? What is happening here is this. So whatever we did, whatever the equations we have here, is that valid? Or whatever we are doing here for this very high velocity, is that valid? I i do not
No,
understand.
sir.
So let's say, let's
Sir, eventually that's the
Sir, no, value of G will keep on changing, right? Because R is significant.
let's
So we can't
consider
use
let's
this.
consider constant G, no
If
problem.
you escape the Earth's gravity, it's more than the escape velocity.
We call escape velocity also. We'll come to that concept later. uh, we'll just try to logically answer this. This is RE, right? This is Earth. I have Earth, and I have some with 64 kilometers, and my cannon is standing here above the hill. Then what I'm doing, I'm firing this ball. Okay, what with which velocity? I have some 200 meters per second. And what this analysis tells us is, it reaches ground. The range is going to be 63 63,840 kilometers. Okay, right? What is the perimeter of Earth? Can you guys guess the perimeter of Earth? It will be 2 pi re, right? So there is one answer, 40,075 kilometers. So you see, I will start here, and then 40,000. If you go back till here, it's going to be 40,075 kilometers, right? So will that happen? Will it go down? Will it turn like this and fall here, or will it go like this? Basically, what would you expect?
It will
So
go straight.
tangential one,
It will go tangential.
like straight.
Straight. It will go straight. It won't
Yes.
fall. But whatever we did analysis is for falling, right? We have a
Yes, sir.
the
So it has more more velocity than escape velocity. It could escape from the Earth.
Yeah, I don't know what is escape velocity. I just have some high propulsion system. I'm just
So whether
firing.
gravitational force of attraction
Hmm.
is a concern in this case, sir?
That is what I want you all to think. Is
Gravitational
there
force of
gravitational force
attraction.
Well,
acting?
G will change, right? Like gravitational acceleration will change because my distance from the center is increasing,
Distance from
and which is significant, right?
no. See, I have this is at 5 kilometers. Till now, what that's what we did
No, no,
for
no,
the
no.
before.
After it fired, after some time, it will go like some significant distance, right? It won't go not ESS,
Will
not
it
like
go on?
that,
Will it go
but
and fall like this?
no, it will go straight.
Straight like this?
Yeah,
How do you decide that? Why do you say it goes straight?
because
sir, it's
the
a
weight
heavier,
of the
but
God is too
very
much, right?
small.
The G of 9.1 changes. We cannot consider as 9.1 constant because of height.
So I have so when I'm firing, my height is same. I just fired with higher velocity. I don't know. So G, let G vary. So how G will vary? G is a function of altitude, right? Is G is a function of altitude? Is that the correct statement to make?
Yeah, you're
Yes.
right.
Right. So if G is a function of altitude, I fired at 5 kilometer per second. Sorry, 5 kilometers. And what we did was projectile motion, and it should keep on falling down, right? Did you understand the concept? I fired in along the straight. Why it should go up? That's my question. I fired it along straight line. You are seeing this as a it was a big exaggeration. It is actually this hill is not that big if you compare with the Earth. So Earth is going to be something like this. Okay, this is the surface of the earth, and my hill is going to be like this. This is the small hill. I just, for exaggeration, I wrote it like this, right? I fired it like this, and what I know is it should go and fall down. But only thing is, I fired with higher velocity. That's all. And what I'm getting is I'm getting L to be around 6,400 kilometers, which means where I will go. So let's say for 40,000 kilometers. So ideally, if you ask me where it should go, it may go and hit somewhere here, right? Or I don't know. So kilometers divided by 600, let's say, divided by 6,000, around 6. If you divide this circle by 6, it should go and fall down here. Why it will go straight outside? So if you are telling straight outside, what you say is you are telling this angle. So this red color arrows is actually this one. This and this are same, but I fired horizontally. Why it should go up? It is acting down.
Yes, sir. Sir, will it form like concentric circle of Earth and the radius will gradually decrease? Sorry, distance will gradually decrease and come to the ground.
Thing. Yeah,
So
that could be
because of the
thought.
curvature of the earth, the height from the ground level will keep on increasing. The G also will be continuously coming down. Because of that, the projectile parabolic motion will not happen.
Exactly. So this is what I want you all to think. What we did is, first you need to understand what mistake we did was, for this problem, this frame of reference. The frame of reference is actually x, which doesn't consider the curvature of Earth. Okay. The reason to make this assumption is I'm going to fire at very small velocity and it's going to drop down, and along this distance, the curvature is going to be very less, right? Is 638.4 kilometers, sorry, meters, right? 638.4 meters, and what I have is perimeter is 40,000. What is the ratio I have? 40,075 into 10 power 3 divided by 638. So it's going to be very much less than 1, right? So this is the assumption we implicitly made while solving this problem. But even the velocity is high, you cannot consider this assumption. The curvature is also changing, right? What happens? So the curvature changes. So what happens? The assumptions becomes, the x direction becomes like this, and y direction becomes like this. So x is, if you put a uh, the surface of the earth, it's going to be like this, right? And then for this, if you calculate, if I fire at, let's say, second, it's going to be going, and then at that time you consider the g variation, and it's going to come and fall down at some point, and that L is given by 6384 kilometers. So what I'm trying to say is, if we fire at 20 meters per second, right, it falls down here. This is still an exaggeration. It doesn't. It just falls down like this. If you consider the uh, like the you say it. If you consider the radius and perimeter of the earth, it's just going to fall down like this, right? So that 680, 684, 638 meters is just negligible when you consider a big whole earth, right? But then if you keep increasing the velocity, it's going to keep on go to higher ranges, at that range what happens, it keeps on comes and drop like this here. So for this velocity, it doesn't mean our answer is wrong, it means answer is right. Only thing is if we should consider in this frame of reference. But anyway, along y direction, so this is also y, along y is going to be in the radial direction, x is going to be along the surface. Anyway, if we consider that, it's going to travel to 36,384. Our analysis didn't say wrong results. But the thing is, it is going to come and fall down in this curvature. But why we need to study this? We are not going to have high propulsive, uh, uh,
Sir,
yeah,
isn't like escape velocity considered in this case?
right. I am coming to that escape velocity. So, what I'm trying to.
One more question
Mhm.
regarding this. Then, how big is too large to not consider this curvature? To what propulsive velocities we should consider or not consider the curvature on the Earth?
So it depends on the velocity with which we throw, right? So when we throw at 20 meter per second, it doesn't matter. When there is a, so let's say if your relation is like this, if it is very much less than one, this is the range you traveled, and this is the uh, perimeter of the Earth. If it is very much less than one, you can have you can have the frame of reference to be straight line, x is along the straight line, and you can do this.
Sir,
But
is it any influence of Kepler's law here between gravitational force of attraction between the Earth
yeah,
center
yeah,
and
yeah.
the mass of the cannon?
True, because it is indeed, yeah, because uh, the Kepler's law just tells about gravity, and what the ball sees is also only gravity. So there should be Kepler's law coming into this picture. But we will come to that orbital velocity, Kepler's law, everything in a minute. But what I'm trying to say is, when I increase the velocity to 200 meter per second, I'm going to go through this projectile motion and hit here. What if I keep increasing?
So, yeah.
If I keep increasing, go and hit here. What if I keep on increasing?
So it becomes a orbit.
Exactly. So I will come and then hit.
Yeah. Yeah. Yes. Yes. Correct.
So this velocity with which you hit yourself at the back is actually orbital velocity. And this orbital velocity is only a function of height. And for this, it's 5 kilometer. Okay. So what this ball is, it's keep on falling. That's all. But it has an initial x component. Okay. So, but since there is a curvature of the Earth, if there is no curvature, let's say, it's going to go and fall on the ground, right? If the Earth is not 6,000, if the Earth's perimeter is not 4,000 kilometers, it is some 4,000 into 10 power 6 kilometers, then it is going to go and drop down on the ground. But because of curvature, the velocity with which we give, as soon as it drops, the curvature also drops, curvature of the Earth. And because it drops, it keeps on falling on the Earth, and finally it reaches the orbital velocity. So once you fire a cannon with that orbital velocity or hitting you at the back velocity, you are no need to do anything else. It's going to keep on rotating and orbiting. It doesn't need any energy to orbit. It doesn't need anything. The gravity will take care of itself. So in the lecture, if you go and rewatch it, we may not have done in this way. Instead, we would have done as a Earth and the Mars, and there is a orbital velocity, and the rotation of frame of reference. There will be a pseudo force, centripetal force, centrifugal force, and again you will end up reaching the same concept. So the concept here I am trying to specify is the projectile motion, which is a freely falling motion. When it is at higher velocity, it becomes a orbital velocity. That is what I am trying to emphasize here.
Sure.
So this velocity now you can calculate, right, with which velocity. But now one thing is we didn't consider air resistance. So let's say this is 5 kilometers, right? So let's say if you keep on increasing to some 10 kilometers, some 20 kilometers, okay, and then you use the same concept and you derive the and you try to get the uh, velocity with which you will hit you at the back, that will be equal to orbital velocity with whatever the formulas you have till now. The formulas which have been derived in the lectures, if you calculate that velocity and if you follow this concept and if you try to calculate this velocity, both velocity will exactly be same. So the important thing to note here, the important thing of the need for this exercise is that it's just this: whenever you throw a ball, it's going to freely fall on the ground, but it doesn't have that much velocity to go over the earth. When you throw the ball with high velocity, it's going to go keep on revolving around the earth. So only uh, force which comes into play in this revolving is only gravity, and that is what Kepler says. Okay, so Kepler's law is also based on gravity, and uh, the orbital velocity, whichever you derived, which will be like, I'm not sure, is it V naught is equal to square root of g m e by r, right?
Yeah.
A plus h or like that. So all these velocities is going to be, it's nothing but the body which is freely falling to the earth. So it will eventually fall, but since the curvature of the earth is also falling, or it is also turning, so it cannot fall to the ground. Instead, it is in a orbit. That's all. So only force which is in the play is gravity. That is important thing which you need to understand it conceptually, and that is why I made this question. So, do you have any doubts in this concept? So, is that clear what I'm trying to
Yeah, it should be
map?
clear.
What I'm trying to map, the orbital velocity and the velocity of the projectile motion and the freely falling system, right?
So I have a doubt. You said that it will continue in the path of orbit. It will not come down to Earth.
True, it won't come down to earth. If you have that initial horizontal velocity, it will never come down to earth.
But that orbital velocity means we have to continuously apply.
Velocity is already applied by gravity. Velocity we applied at the start. Okay, so no one knows how Earth started revolving around Sun, and no one knows how Moon started revolving around Earth. But Earth, Moon, everything has orbital velocity, which was obtained at the formation of this galaxy, Big Bang theory, all those things. When it was started, this velocities has been imparted on the Earth and Moon, which allowed it to continue to stay in this circular motion or elliptic motion of orbits. Okay.
So, for example, satellites, when we taken into orbits, will it be fired to a particular orbital velocity, designed orbital velocity?
Right.
How it will be fired?
True. So it is indeed, it will be fire. That is the delta V calculations we make. So the delta V total velocity requirements to reach that altitude, and in order to stay in that altitude, you need to impart a horizontal velocity, which is the orbital velocity, in order to make it continue in the orbit. If not, it will come and fall down into the earth. So that velocity is given by the rockets. So when we launch a rocket, what happens? Initially, it will be in the ground, and if you just compare the energy requirements, if you, because conservation of energy is valid everywhere. Initially, it will be in the ground with potential and kinetic energy, right? Uh, Zero, and I need to do some work to reach the orbit. Okay, but if you just go and put it in the orbit, it's not going to rotate. It will just
Yeah.
fall down. Okay, but if you once you go to the orbit, you have to give a thrust.
Velocity.
You have to give a force. Using the force only, you will have a you will impart a velocity. When you impart a force on it, on the satellite, satellite will gain velocity. And once you reach after going to that altitude, you have to impart that velocity, orbital velocity, in order to make it stay in the uh, orbital motion.
Orbit. Yeah.
Right. So, uh, sir, still not clear. So there is one question, still not clear, why does body resist escaping the orbit when we know that orientation of escape velocity doesn't matter? So 200 kilometers per second is large compared to 11.2 kilometers per second. How do we expect the ball to orbit? Right. So, uh, so we need to understand what is 11.2 kilometers per second. How do we get 11.2 kilometers per second? So if we get, so this velocity is nothing but on the earth, you have some,
So when an object becomes independent of the angle of projection,
mhm,
that's when you reach 7.2 kilometer per second.
meters per second. So you will just fire something out with some energy 11.2 meter per second, and it will keep on and it will go out, right? That is what you are trying to say, right? It will escape the earth. It is true. Now for this case, 200 kilometers per second. Huh. For this case, I'm not telling it will come down, but what I'm trying to say is if the velocity is less than orbital velocity, it's going to come down. And if it is equal to orbital velocity, it's going to revolve. And if it is greater than, so let's say if it is greater than orbital velocity, it is going to go out like this.
Sir, like if I'm not wrong, like for example, like some satellites also fall down. So they fall down
True.
because their orbital velocity is like less than the required. So that's why they fall down. So that
No.
is the thing that
So
trying to.
yeah, so actually some satellite, what happens is, um, uh, what we consider here is simple G, right? So
Yes, sir.
this G is going to change when you are in orbit,
Yeah,
because
yes, sir.
Earth is not sphere, it's a little bit oblate, right?
Yeah, yes, sir.
So because of that, G keeps on changing, and it is something called J2 perturbations, which will be a little bit advanced. So,
Okay, sir.
uh, so if you because of that, you cannot exactly um, tell that this is orbital velocity. So when it comes to the high gravity place, it's going to get accelerated more and it comes down. So that's
Okay.
why satellite inbuilt has this correction thrusters within it,
Yeah,
which
yes,
will
sir.
help it to adjust and put it in the orbital velocity. It doesn't mean, I told that if you just put it in the orbital velocity, it's going to keep on rotating, revolving.
Yeah.
It won't come down. I told that, but it is based on the assumption that G doesn't change. G in the
Okay.
sense gravitational G me by RE doesn't change, right? But in reality, it's not going to happen. And another one, this all these calculations is for two body problem. So there is Earth and there is satellite, or there is Earth and there is a moon. But what happens is this satellite also experience gravity because of the moon. So
Yeah,
these
yeah.
three bodies, when they come into picture, what happens? The velocity is no more the orbital velocity, so it has to keep on correcting the velocity in order to stay in the uh, orbit. It is true, but here based on, because of lot of these assumptions, I am telling that it would be in motion. So is that clear?
Yeah, yeah, sir. Clear.
Suppose, for example, you consider an asteroid moving in a straight line. Asteroid doesn't have orbit, so it
So
moves in a
actually,
straight line. Let us say.
uh-huh. So asteroid, Rajesh will come to that. I will come to that. So asteroid, what happens is, when something is in motion in space, it is actually in orbit of something. Okay. So let's say there is this Mars and there is this Jupiter. In between, we have a lot of asteroids. We used to say it is asteroid belt and all, right? So in this asteroids, it is actually in orbit around the sun, or it might be orbit around the Jupiter, or it might be orbit around the Mars. So it also indeed has orbital velocity with it. It is not in a deep space. In fact, in deep space, what happens? It's microgravity. Like gravity would be very small. But considering the mass of this asteroid, right? This mass of asteroid is going to be very much bigger than the human mass. Okay. and mass of the Jupiter and mass of the Mars, these are all going to attract with each other, and it is going to be in a motion, or if you have simply put, it will be freely falling towards the gravity. But which side has more gravity? It is depends on the mass of the Jupiter and mass of the Mars and the position in where this asteroid is. So basically, we can generalize this gravity as a gravitational field where it keeps on varying, and that's what if you would have gone through the lectures, we would put something like this, and this is the field, and if there is a heavy object around that, the gravity, the space time or the gravity field is going to be more attractive, and if it is the planets are not nearby, it's going to be more or like flat. So this gravity field, this is called field because it is present everywhere, and each and every planet is going to have its own field. And if we generalize it, this gravity field is what going to determine the motion of asteroids.
So this gravitational constant G minus 6.671 into 10 to the power of minus 11, is it applicable to entire space, including like deep space, vacuum and other thing? Or it is limited to only Earth side?
Right. So for that, we need to understand from where this G came.
Yeah.
Before understanding, we cannot say anything. So let's write. This is the Newton's law of gravity, right?
Yeah. The RE plus H.
So this is the Newton's law of gravity. Newton's law of gravity is with only two bodies. One is mass, and another is mass of Earth, or like only two
Okay.
planets.
Yeah.
So for this, what is the gravitational constant is given by G. It is not true for entire space.
Okay. Fine, sir.
So, but it would be true for
But
all the
in
two
deep
body
space,
systems.
a body is moving. How it is moving? With what gravitational force of attraction? With what reference it is moving? Uh, I'm just asking in terms of problem solving. In deep space, a mass is moving with some velocity x in a straight line or whatever it is. So how it is moving? So whether it is mm, so I want to know, exactly understand what is that.
Sure. So, in deep space, what happens when, let's say, the Mars is moving? Mars is moving means there is some gravity which is pulling the Mars,
Correct.
and that gravity is actually from the Sun. That's what we see, and
Okay.
also Jupiter. So Jupiter also exerts, but we can say generalize and say it is Sun is going to exert the gravity, and based on that motion, it is going to move. And one more thing is, it is not just Sun is going to exert. Jupiter also exerts. Earth also exerts. Surrounding asteroid also exerts. If the Mars is exerting a force on asteroid is going to exert a force on Mars, but its magnitude is very less, so we can tell that Mars is attracting the asteroid. Or
Okay, fine. So in such case, gravitational force of attraction can be calculated like the mass in the deep space and mass of the sun. Am I right, sir? Yeah, like
can you
what
come
you have
again?
given G, see F is equal to G into M into ME by RE plus H. So this G can be calculated. Instead of ME, we will put M sun. M sun and in the deep space. Mass of the sun into mass of the body divided by radius of the sun plus, whatever the height, something like that.
So this you can completely write. So mass of sun by radius of sun plus altitude. We can completely write. This is true, but for a two-body problem. So
Sir, whether
before
this
Kamal,
equation is
Kamal, could you please wait? I will ask Rajesh. Rajesh is raising hand. Rajesh, Rajesh. You are in mute.
It in mode.
Hello, sir.
Yeah, yeah. Rajesh, please go
I
ahead.
have a small doubt, sir, regarding the orbital velocity. Sir, when I send some object into the orbit, we can consider the mass of the object.
Good question. Right.
Yes, yes, sir.
Yeah, good question. So it thinking of how do we explain this. So what we have is the velocity with the orbital velocity, as you said. The mass of the
Yes, sir.
object is uh, let it be whatever be the mass, right? Uh,
Yes,
uh, what happens is when you do a force balance calculations, the mass comes into
yes,
picture, but it gets cancelled out because we consider only one mass. So, for example,
yes,
uh, uh, if you consider a satellite or some small body with mass m, it is going to move around with a big mass m, right? So there's going to
yes, sir.
be force of attraction, right? And there's going to be this orbital velocity.
Yes, sir.
So if we calculate, so if we go with the concept of centripetal force and this thing, it's going to be m omega square r is equal to g times m m of earth divided by uh, m gets cancelled and omega r nothing but v, right? Orbital
Yes, sir.
velocity times omega, right?
Yes, sir.
So it actually doesn't depend on mass. I mean mass.
Yes,
So
sir.
when you put the orbital, when you put some mass, whatever be the mass, when you put the it in some altitude, so orbital velocity is only a function of altitude, right?
Yes,
And,
sir.
but in order to reach that velocity, you need some forces, right?
Yes, sir.
That force depends on mass because
Yes, sir.
a simpler, let's say 10 kg satellite you are putting, it's going to require less amount of energy to reach that orbital velocity than a 100
Yes, sir.
kg satellite, right?
Yes, sir.
Orbital
Yes.
velocity is not a function of mass, but the energy which you need to put it in the orbit is going to be a function of mass. So you
Yes.
are right. Orbital velocity is not a function of mass.
Yes, sir.
It's only is the function of altitude. At this altitude, what is my gravitational pull? In order to uh, stay in the orbit and in order to be in the consider the curvature based on the curvature, I should be in the orbit. In order to be in that orbit, what is the velocity? I don't. It doesn't. What is the mass? I am. What is the mass I am?
Yes, sir. Thank you, sir.
I think
Sir,
Kamal.
in this formula, G m into m sun by r radius sun plus h. Whether G value can be taken as like minus 6.11 into 10 to the power of minus 11, applicable to sun also. And I don't know the value of h because some object moving, we don't know exactly from where from which orbit from the sun it is going. We don't know. So in such case, h how I can take an object is moving in deep space in
Okay.
some straight line.
Hmm.
So whether two questions is one is g can be taken as 6.61 into 10 to the power of minus 11, and h I don't know. That is the height of the orbit at which the object is moving. I don't know.
So,
So
if you were expected to calculate the velocity, orbital velocity, then you
mhm.
need all these parameters. But for the sake of completion of your question, the 6.61 is valid for any two body system. Okay, Newton's,
Including sun. Yeah.
yeah. So Newton's law of gravitation just tells about two body system, and for this two body system, this g is constant. Whatever the two body, let it be, doesn't matter, it's just g m1 m2 by r square. And number two, h should be given in order to compute the force. If h is not given in the deep space, what happens? There is no gravity. In
Yeah.
fact, in the deep
Yes.
space, in the sense, whenever we say deep space, it's the gravitational forces or gravitational field is zero. There is no gravity acting on the body. Then if
Yes,
you
sir.
want to just define the deep space motion, it's just going to be Newton's law. Let's say if you want to calculate momentum of a body which is in a deep space motion, it's going to be just mv. Momentum is not
Okay.
going to change. That the definition of momentum is not going. Definition of impulse is not going to change. Everything is going to remain same.
Okay.
Only thing is, whenever there is a application of forces and when we were asked to calculate the motion of a body in the
Yeah.
presence of these forces, then only we need to consider Newton's first law and second law. We need to apply it carefully in order to get the results.
Right, sir. Thank you.
Well, Kamal, you had some question?
Okay, sir. I just want to know that, okay, your the discussion, this is whether this particular formula is universally, it's okay, it's all called the universal gravitational law. So gmm by r square. I thought, okay, it is universally applicable.
It is universally applicable, but only for two body system. It doesn't consider three body system. So in case of
Okay.
three body system, there is a slight modification in the uh,
Half an hour waste.
in the force, gravitational force. It will almost remain same, g m1 m2 by r square. It will almost remain same, but there will be additionally m3 also. How do we take care of that? m1 m2 m2 m3 m3 m1. So those combinations
Maybe,
comes into
maybe you have
picture.
to calculate maybe you have to calculate the force for M1, M2 and M2 and M3 separately, and you have to resolve the forces to get what are the forces between all the interaction of these three
True,
forces, right?
true. So in
Something
a
like that.
body,
Yeah.
what are the gravity forces acting? So due to body 1, due to body 2, due to body 3, what are the gravity forces acting? And these three forces will tell you, these three forces, if you apply it in the Newton's second law, it is going to tell you the motion of the body. That's all.
Okay.
True, completely
Thank you.
true. And one more thing I want to tell here is, everyone, you no need to call me sir, you can call me Ganesh itself. Uh, be little bit good if the conversation is instead of sir conversations, Ganesh would be better. So I prefer that. And actually, I have a few more questions to complete, but I think I covered most of the concepts in this itself. Third question, anyway, I will post. Please try to solve this question and try to question yourself about the concepts. That way only we will try to learn the concepts better. And I have few more questions also. Um, one is based on based on geostationary orbits. I think it is fairly, you need to apply the equations here and you need to solve it. Uh, and similarly, I have another energy calculations question. Uh, Maybe what I will do, I will solve this and I will post it. Supply it. It will be in your NPTEL course website, so you can go and look it at. Maybe I will solve all other three questions also, and I will post the solutions. And if you have any doubts, you can come back and ask me. So it's around, we are approaching the end of the session. You can stay back and ask me any questions, or anyway, I will share all these notes with you, and please try to solve it. It will be helpful in understanding your concepts. All right, by
Sir, one
this,
question I have.
please carry on.
Yeah, actually, initially we are discussing about impulse, and you told that it is change of momentum.
Right,
But okay, okay, and we are discussing about a ball which is thrown and it is making a projectile and hitting the ground.
right,
But okay, when we are in schools, we are told that impulse is force into dt, a very small time. When dt increases, that is the impact time increases, then impulse also will go up or down. But here, we are only talking about a projectile motion, and at the time of hitting the ground, there only the impact happens. Then only the impulse also is created. So that time is not given in the problem. So how to consider that, and whether it is exactly the change of momentum, or it is something else.
Uh, so if the time is not given, you cannot calculate the uh, force. To calculate force, you need to know the duration of time it has been the impulse has been applied. So impulse is just change in momentum. It has nothing to do. So that's where we wrote this equation. So
So it is
change in
nothing to
momentum
do with
is
the
impulse.
impact time, right? It is
Huh.
nothing to do with the impact time.
Nothing to do. So in coming to that question, so one impulse we applied is when we fired the gun, right? When we one impulse has been applied on the ball, right? And then it has came, and when it drops down again, there will be one more impulse. True. So again, there also we need to know the time in order to calculate uh, the what do we say, the force, right? So but for calculating impulse, you no need time, because it's just change in momentum.
Okay.
Because force is rate of change of momentum. So few words are important. Rate of change of momentum. How this change of momentum is changing with respect to time is given by force, and this change in momentum is just the impulse. So rate of change, you cannot say rate of change of impulse, but impulse by the time you applied, it's going to be the force.
Okay,
Impulse
I
by time.
understood based on the formula. It's a rate of change of momentum into the rate. So, it is only a change of momentum. So that's how it comes from the formula. But understanding impulse itself, so where we are talking about the impact time only, because in school and all they say, when you throw a ball and I'm catching the ball, when I drag the hand along the line of along the vector, then the time of impact of the ball will increase, and because of that, my impulse also will go up. So something like that. That's what just for thinking whether it has an relation with the impact duration. Okay,
So
right.
yeah, 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 I
We
understand.
made it
So
clear, sir.
yeah, yeah,
Made it clear.
yeah. Maybe I will be little bit clear here. So when you are catching the ball, okay. So do you have time? Can I explain?
Yeah, yeah, yeah.
So when you are catching the ball, it is going to come and hit you with some velocity, right?
Yes.
Some
Yeah.
velocity. It's going to come and hit you. Let's say you are stationary. You are stationary. You are catching the ball. So what happens until it comes and hits you, until the velocity is 0 meters per second, because as soon as you catch it, velocity of ball is 0 because you catched it. It's going to become stationary. During this duration is where the force is acted, because that's when the change of momentum has happened. After you catched, there is no change in momentum.
Okay.
So during this delta t only impulse has been applied. So this delta t cannot change, because as soon as you catched, its force has been applied, and there is no such thing like catching. It's just you will catch, because the action of catch is just a small time, right? So it will be
Okay.
millisecond or so, right? During that one
Yeah.
millisecond, how this ball has changed to some velocity to 0 meters per second will give you the impulse, and that
Okay.
impulse into this millisecond of catching will give you the force. It's not like you cannot keep on catching. Like how can you keep on catching, right?
Okay. Okay.
once
Got
you
it, sir.
once the velocity decelerates to 0, that's the end of application of force.
Okay.
So that's the end of impulse. So that I don't
Okay.
think so
Gotcha.
you can control it. The delta t you cannot control it. Only thing you can control is the force, the change in momentum. If the velocity comes with very high velocity, instead of 1 meter per second, if it comes with very 5 meters per second, then upon decelerating it's going to exert more force, and that delta t is going to remain same because it's going to decelerate to 0, and because of that there's
Okay.
more force, there's no more impulse on your uh, hand. That is the only
Okay.
difference. So it
Okay.
is true
That
that
is
when the delta, if on seeing the formula, you can say that when the delta t changes, my impulse changes. That is true, but actually delta t has doesn't have big control. You don't have big control on delta t. You have full control on velocity.
Okay.
That's what I'm trying to say. So is that clear?
Okay.
What
Thank you.
is that what you are hoping for, or
Yeah,
something else?
yeah, I got it. Got it. Because we cannot change delta t, so we
Hmm.
are changing delta v, and that
Yeah,
only has an effect.
yeah. That's all. That is only have the effect. As per the formula,
So,
it is true that when the delta t changes, impulse changes. True, but we cannot have more control on it in situations.
okay.
Does anyone have any more questions?
So one more thing I wanted to ask, like I'm like clear with that orbital and concept with when the velocity was increased.
Mhm.
I'm just wanted to ask, like the time was same, like we find out the time was same, but like if we practically think, like shouldn't the time be like increased, or like because the velocity is increasing, or it should reduce, like because the velocity of the object which we are like throwing, it is increasing, so like shouldn't be there a change, slight change to like time value, but we find out it was no change.
So actually, ideally speaking, uh, is this time you obtain considering it is a straight surface, right?
Okay.
And the time, how do you calculate time? Time is calculated from the y when it reaches the bottom, right?
Yeah, yeah.
And that is calculated by, that is coming from the gravity. Gravity is only pulling it. So the
Yes.
rate at which it is pulling is going to give you the time. So that time, you actually don't have control. It is just acceleration due to gravity, and the time is going to remain same. It has nothing to do with x velocity. That is what we saw, right? So
Yeah, yeah, so we solved it, yeah, like
dx is equal to constant. It is
yes,
not dependent on time,
yes,
right? And one more thing is, again, I would like to emphasize this is assuming that surface is straight,
yeah,
right? So for
it's
200 kilometers per second, as one of you rightly said, I think it is far greater than 11 kilometers per second. It should go out.
yeah, sure, sure, yes,
It
yes,
is in. It will indeed go out, but that for 200 kilometers per second, whatever value we got is for having a straight surface. But in our Earth, it's not straight surface. The curvature is keep on happening.
yeah, it's the
So,
curvature.
so this analysis kind of breakdowns when where you cannot have analysis on the curved x direction, right? It is little difficult to have analysis on the curved x direction, but
Yes, sir.
the concept is you had to have a perpendicular velocity to the gravity. So this is gravity is on y direction, perpendicular to the gravity, or you need to have a very high velocity in order to maintain that in orbital, in order to maintain that in orbit. So that is the concept I want to emphasize. That's why I came up with this fictitious, uh, you know, example which considers surface to be
Yes,
flat, and I was able to explain you how it become the how the projectile motion can tell you the orbital velocity. It's just
yeah,
that's the only uh, aim I had. So yeah, so I feel like you understood the.
yeah, yes, yeah, yeah, I understood.
Sir, adding to this question, this 11 kilometer per second,
Mhm.
what are you talking escape velocity? Like for example, this is only on force we are imparting at when you are throwing a particular object. So because of gravity, this velocity will be keep on coming down,
Yeah,
and it is not constantly imparted 11 kilometer per second or
yeah,
whatever 200 kilometer per second.
yeah,
So
yeah.
in that case, whether we can say that this 200 kilometer per second will exceed the escape velocity and get out of the gravity of the Earth, because the velocity is not going to be 200 kilometer per second at maybe a distance of 10 kilometers away from the point where we have imparted the velocity.
Exactly. True.
So that also should be considered while we are whether
Yeah,
in that
because
case,
it doesn't have
yeah.
any propelling device. Yeah, I guess. Yeah.
Doesn't have. It doesn't have. True. So that's where. So since we cannot have the, we cannot do this analysis when there is a curvature on Earth. That's where what we did in the class, in the lectures, is to have these two rotational frame of reference, right? So there is this uh, this so I will come to the question. So I wanted to emphasize this also. So so this two rotational frame of reference x dash and xy, right? So here what happened, um, here so we consider one more frame of reference on the body, and we said this is accelerating phase, so we need to there's going to be gravity force acting, and then there's going to be pseudo force, which is a centripetal force acting, and based on this calculation you are going to get the orbital velocity, right? But what happens is, coming to the Kamal's question, when you throw the velocity, when you throw the uh, any object with some 11.2 kilometers per second, what happens is, as it goes out, the velocity keeps on decreasing, because that body is keep on getting attracted towards the earth by the gravitational force. But what happens is, there is a layer, there is this atmosphere after that, so what we also know is, this gravity is a function of h, right? So as altitude goes, this gravitational attraction is also keep on decreasing. So let's say if we see the gravitational equation, me by r square, right? So as r increases, my fg is going to decrease, so the attraction is keep on decreasing. As soon as I reach 10 kilometers per second, the attraction has decreased, but still there is an attraction. But the velocity 11.2 kilometers per second might be reduced to 10 kilometers per second, right? And from there it again keeps on moving, because 10 kilometer per second is in the radially outward direction. It's going to keep on moving along the 10 until it reaches 0 meters per second, 0 meter per second. It is going to keep on moving, right? So it will keep on moving till it reaches 0 meter per second, and when it reaches 0 meters per second, or it may not be also, it would have escaped the gravity of earth. That's why it is called escape velocity. So anything which is fired below escape velocity, let's say 11 kilometers per second, it will go reach the atmosphere, and then since it is affected by gravity, it reaches 0 there at some altitude, and then it comes back. So the velocity is indeed changing along the direction of the motion of the body, but the thing is, it hasn't reduced to 0 within the gravitational field of Earth. So that's why it is escaping the Earth's velocity. So maybe what you can do is, you can do that calculation. So um, let's say you are firing something at 11 kilometers per second, and let's say what do we say, let's simplify this assumption, like you are firing vertically up. Let's say you fire at 10 kilometers per second, and simply do, so this is the ball, and that ball be some 5 kgs, and let's say you fg is equal to minus this is ma, fg is equal to minus fg, which is equal to minus mg. So acceleration is minus g you make it as a function of h, right? And then you integrate it. So a is dv by dt is equal to minus g as a function of h, dv is equal to minus g as a function of h times dt, because h is also varying, like altitude is keep on increasing as you go up, right? And then you do, let's say some t equal to 0 to 1 seconds, or some t seconds, and see how the velocity has varied. So when you do this integration, you will know that this v2 won't be equal to 0 at some altitude of, let's say, 100 kilometer per second, is where 100 kilometers is where you will feel the effect of gravity. Or let's make it more also. Let's make it 1000. I'm not sure at which altitude you won't feel the earth gravity, but in case if you know that altitude, you can check for yourself whether that altitude has reached when the velocity, and for that altitude, what is the velocity you have. It may not be, it won't come to 0, or it won't have decelerated to 0, and that would be the reason, because it escapes the velocity, it escapes the earth's atmosphere. It is indeed decelerating, keep on, but it hasn't decelerated that much to come down. That is the reason, and the reason is it has very high initial velocity. That's all.
And G's value is like attract force of attraction is decreasing.
Forces keep on decreasing because it is inversely proportional to r square.
Yeah, yes.
One basic this mathematics question.
Mm-hmm.
Like when you are integrating the previous time also 9.81 into t in the vertical component. Normally when you are integrating there should be an constant, right? Normally we'll put plus c1 or something like that. So
Right, right.
that one is not seen here. Why that constant is not coming, or how it is getting equated to zero?
So, so we will add constant only if it is a uh, indefinite integral. So when I say indefinite integral, let me explain you that. Uh, we have two kinds of integral which can have the let's say let's take this. What we have is was that dv integral of g times t dt, right? This is the equation you have, right? So I think it's minus anyway. So if we integrate it, minus gt square by 2 plus c. This is true if it is a indefinite integral. So what is indefinite integral is it doesn't have any limits from here to here, from here to here. It doesn't have any limits. Let's say if I have the same velocity, but I know what is the limit. Let's say I want to see only from 0 to 1 seconds, and I need to know my initial velocity is 0 and I need to know the final velocity vf. Okay, so if I have something like this, then I will integrate this and I will write to minus gt square by 2, and t varies from 0 to 1, right? And then instead of v you substitute this final minus initial is equal to minus g by 2 times t square, which is 1 square by 2 minus 0 square by 2. This time you do not have plus c, so I do not add plus c, because this plus c you shouldn't add because you already have the uh, limits. So this is called definite integral. So then there should be one more question. So when should I do definite integral? When should I do indefinite integral? Right? So maybe if I don't do definite, what will happen? So now let's say you have. So if till here is the concept clear? Come on.
Yes, clear, clear, clear.
So when with definite integral means we have limits. Okay. So here
Okay.
we have v final is equal to minus g by 2 into 1 by 2, right? Which is equal to minus g by 4, right? Now here we have one more equation which says minus g t square by 2 plus c. Okay, we don't know what is this plus c. How do we find this plus c? On the known value, what we know is at t equal to 0, we know that v is equal to 0. So you substitute this in this equation. What happens? 0 is equal to minus g times t, which is 0, divided by 2 plus c. So what it turns out is c is equal to 0, right? So now I again substitute in this and I will write the final equation to be minus g t square by 2. Now what I need is I need to find what is the uh, velocity at 1 meters per second, right? Now if I substitute it here, velocity at t equal to 1 meter per second is equal to minus g into 1 square by 2. So you wait 1 second. You should end up with the same results, right?
Yes.
Why I'm getting different results?
That you put the two twice inside the bracket also. You have put.
Ah, right, right, right. So right. So then this becomes minus g by 2. Similarly, we have minus g by 2. So the difference between these two approaches, v we actually did this, maybe with different color. We actually did this as a uh, here. We inputted the limits into the equation itself, right? The
Yeah.
here we assume that we don't know the limits yet, and we integrated it, and then based on the known value, we found that integration constant c. That is the difference between these two, but both should give you the same results. Anyway,
Okay.
when you use a definite integral, you don't put c. It doesn't mean you should follow this approach. You no need to. You can follow this approach also. You should get the same results. Integration is integration.
Okay. Thank you.
Thank you. So I think I missed a lot of questions in the messages. But G indeed unpredictable. Yeah, Varun Kumar. I don't know whether he is here, but it is indeed unpredictable. Uh, so how do we calculate mass? Okay, it's a different question. I will get back to you. I don't know whether he is here or not. Then we have. May I know what did for your bachelor's? I'm currently doing mechanics. If someone like me who is also interested in doing PhD in aerospace field. Well, I am. I did mechanical bachelor. So, mm, and if you are interested in aerospace field, you can pursue your PhD in aerospace field. What you give someone? Um, I'm not sure. What I would say is you better clear understand on your concepts. So that is what very much important when you do a PhD. You cannot fool yourself with knowing partial concepts. That's all. So maybe we will talk later. Uh, Kamal, do you have any questions? I saw you raising the hands.
No, that's by mistake. Sorry.
Okay. Thank you. So can we get your mail?
Thank
I
you.
have some doubts related to career paths in aerospace. Maybe yeah, you can. I will help whichever I know. Uh, mhm. Yeah. So if there are no more questions, maybe we will close this. I will post this session in the YouTube also. You can go and visit. I will share you the lecture notes, whatever we did till now. Uh, Please try to attend the next class of one more uh, session, which is on tomorrow. And uh, please try to attend all the classes or all the sessions we will have in every uh, week. Okay. So, yeah, thank you. Yeah, Devansh, do you have any questions?
Ganesh, how will you be sharing these PPTs?
So there will
Just
be this. You have the NPTEL
yeah, yeah, yeah.
the live sessions, and there will be one more. Yeah, I think there is a live session option. So there you will get. There it will be updated.
Okay,
So
got it.
I will upload in the drive, and I will share you the links. Um,
ठीक
or
है ठीक है.
yeah, you can even put it in the common group, right? You can. There is this NPTEL common forum. You can even put it in the forum. Maybe
Okay,
I will share you the links in forum also.
okay, perfect.
Thank you,
Thank you.
everyone. I will close this today.
Thank you, sir.
Sir, thank you so much.
Thank you, sir.